Okay, so this time around, we continue looking at functions with several variables and we're getting limits still. And we're going to look at a series of examples to just make sure that we understand how this works. So the first example for tonight is going to be something very straightforward. So if the function is continuous at that point, all you need to do is just substitute and this is going to work out. So let's pick a basic one. We have at the point 5, 1, and then you have a function x, y over x plus y. For this one, we see that we have no complication. You can never get a 0 here. You can never get a negative under the root. So we can easily just substitute. We're going to have 5 multiplying 1 over 5 plus 1. This is going to be 5 over 6 as our limit. So this one was straightforward. We had no complications whatsoever. So evaluating the limit was very easy. But in some cases, we might need to use some tricks. And this is going to be the case for the next example. In the next example, we want to evaluate the limit as x, y approaches a point 1, 1 for a function 2x squared minus xy, then we have minus y squared. This is over x squared minus y squared. What we quickly see here is that at 1, 1, the function is not continuous. That is because if you substituted, this would be 2 minus 1 minus 1 over 1 minus 1. This is going to be 0. So at the point where we want to see the behavior, the function is not continuous there. So, but does the limit really exist? Or does the limit exist at that point? That is what we want to see. So for this one, to see if the limit does exist at that point, we can just see if we can simplify this expression. Well, the numerator seems to be some function. We can see if we can factorize that function so that we can write it in terms of x and in terms of y. So what do we have there? Can we try to see if we can see this a little bit quick? Well, the denominator seems to be something straightforward there. The denominator seems to be coming from a difference of 2 squares. So we can easily look at the denominator as x minus y and then x plus y. This seems to be what we see from the denominator looking at the structure. That's a difference of 2 squares. But how about the numerator? So how can we deal with that numerator? Well, we can actually look at it as something we can even look at it in terms of factorization. Can we factorize this expression? Weird, for a function of 2 variables. Can factorization here actually work? We do have that cross product term, so factorization seems to be a little bit tricky, but let's try the ordinary way of factorizing something like this one. Well, here we have 2x squared, y squared. So I want to find 2 terms. When you multiply them, they give us that. When you add them, they give us the middle term. Let's see how weird this is. We usually use this for single variable functions, quadratic functions. Because this, above all, when you look at it, highest power is a square, a 2. So this is still quadratic. So I see that for me to achieve this, I need xy and xy. When I multiply xy and xy, I do get xy squared, x squared and y squared there. That's what I get if I multiply those. But if I am ever going to get a 2 there, one of them must have a 2. So if I am going to get this 2 here, it means that either a 2 must be here or a 2 must be there. Above all, the product, since this is positive and this is negative, the product must have a negative here. When I multiply the first term and the last term there, the product must have that negative. So one of them must have a 2 if I'm going to multiply and get that 2 in place. And other than that, when I look at it, So I can set this to be the 1 with the 2, and I set that to be my, it doesn't matter anyway, since this is basically the same thing. All we want is when you multiply this, you will get that with the negative. When you add, you still get that. I feel like I could have done this in an easier way. The thing that, of course, I'm getting the same thing there. I feel like I could have done this in a much more easier way. But anyway, this works. So I have 2x squared. Then I can say plus xy. I can say minus 2xy. And then I'll have minus y squared. So what is common between these two, I can factor out x. What I remain with is going to be 2x plus y. And then I factor out what is common there. There's a minus present. So I'll factor out minus 2y, not 2y, just minus y. What will remain here will be 2x and plus what will remain is 1y. There will remain. So now I have x minus y multiplying 2x plus y. This worked. Oh yeah, it did work. And if you try to expand this, you should see that it will go back to that expression. This ended up working. So just for fun, is there a simpler way you could have approached this to arrive at the same factorized expression? It should be. Yeah, looks like there's nothing. Okay, so we reached this point. So what does that imply? The limit we're evaluating can now be seen. Yeah. Go ahead. Okay, so one more time for him. So first thing, same way that you factorize ordinary expressions, I multiplied this with the last term together with the sign. So I ended up having minus negative 2x squared y squared. So two terms, when I multiply, I get this. When I add, okay, so when I multiply, I get that expression. When I add, I get the middle term there. So I see that for this to be possible, both terms must have xy and xy. But to get a negative, one of the terms must be negative. It doesn't matter if I give a negative since this is the same term. But if I am going to get a 2, if I am going to get a 2 here when I multiply, even when I add, for me to end up with that, one of the terms should have a 2, either a 2 here or a 2 here. One of them. But if I want a minus to be here, when I subtract, it means that the 2 must be with a negative term. So that when I add these, I'll end up with minus xy, which is the middle term. There's a question? Someone was saying something? Okay, so are we okay with this part here?
Yes, sir.
Okay. So now you can go with 2x squared, and then I'll have minus the first term there, minus 2xy. And then the second term, that's plus xy, then minus y squared. So now what is common between these two? I see 2x is common. When I factor out 2x here, I remain with x. When I factor out 2x here, I remain with minus y. For this part here, what is common? Y is common. So I'll factor out y. What will remain when I remove y here will be an x. And here only y will remain. So now I have 2x plus y when I get this and this. And in the brackets, we have x minus y. So there we have it. We'll factorize again. So having done that, we can now get our expression. So if you recall in last night's class, I did mention that there will be situations where you need to first factorize. In some cases, you need to basically complete the square. That is if factorization cannot work. You might have to complete the square. But completing the square mostly works when you don't have that cross part thing. When you don't have this, you have maybe 2x squared, maybe the x, then y squared, and the y, but not the cross product. Once you have the cross product, the factorization cannot help you in trouble. Okay, so you have ln x and ln pro. There's a question? So the numerator in the factorized parts, x and y. So x minus y in the numerator and denominator cancel out. So now we have the limit as x comma y approaches 1 comma 1 for 2x plus y over x plus y. Now we see that we can easily substitute here. When we put one where there's x and one where there's y, we end up with 3 in the numerator, 2 in the denominator as our limit. Any questions there? Okay, so hope you found that interesting. I did find it interesting. So let's get another question.
So,
Yes, please.
could you solve some one question from the tutorial sheet?
Let's see the tutorial sheet. So let's look at a few from the tutorial sheet as requested, and here evaluate the following limits. We're going to pick from this category. So what do we have? The first one is it's straightforward. Let's see what's there. We have the limit as x comma y approaches 0 comma 0. And then we have cosine of x squared plus y squared, y to the power 3 over x plus y plus 1. Now, I do remember she did say, can I solve one question from the third sheet? I found the easiest question in the third sheet. I'm going to solve it. Then she should be happy. Right?
No, you probably solved the other as we go.
Say one question from the third sheet. Okay, so let's have here. So for this one, since we can easily substitute, function is continuous at that point, we can easily do that. So this becomes just cosine 0 plus 0 over 0 plus 0 plus 1. This is cos 0, which is 1. Done. So that one was very straightforward because the limit, the function was continuous. Okay, so let's pick another one here. So evaluate each of the following limits. So we've done this one. This was a simple one, easy to work. So let's find another easy one to work out. So let's see, easy one to work out. The others don't seem that easy to work out, but let's pick. Looks pardon? Pardon? What are you saying? You understand E? Why? Is it because it looks weird?
No, because I'm seeing something being undefined there. So it's
Something undefined. Don't you say it's the same undefined even here?
but I want to know how to handle the magnitude there.
Okay, we'll see if it will show up. Okay, so what do we have? We can pick, let me see, do we have the ones that require us? So you have to be very careful here. Some of these expressions, if simplification cannot work, then we have to see if we can show that it actually doesn't exist. But if we end up in the situation where we can't simplify to show that the limit exists, and we can't prove that the limit does not exist, it will imply that we might have to use the definition of the epsilon delta, the definition of a limit itself. So you have to be very careful. I'm looking to see if there are specific questions where we have to do that, and I am not seeing those questions. So implying that those questions must be part of this. So we have to be very careful not to tamper with those, because those will be special. We'll look at them later. So let's see if this is something we can easily discuss. First thing, I'll still try to see if it is defined at that point. So is it continuous at the point? So we're basically looking at this. Since this is a 4, this is a 3, this is a 1, we're seeing a problem there. We're going to have a 0 in the denominator. So we have that 0 in the denominator. Because we have that 0 in the denominator, we need to see if we can simplify and then get the limit. Do you see the trick you need to use here? Initially, when I was speaking this question, I didn't know as well how we're going to proceed with it, but I saw square roots. I saw it looked heavy, it looked complicated. I knew it would simplify. Somehow it works like that. For this one, when I look at it, I see there are no negatives, there are no square roots. It kind of seems like I can't simplify. So when I try this one, the thing that comes to my mind is maybe the limit doesn't exist. So I'll try to show that it doesn't exist. That would be my approach to this one. But when I looked at this one, it feels like it can simplify. How would you simplify it?
I can just let show the numerator.
Exactly that, yes. First, to start by rewriting it to make sure that it makes sense for everyone. So we have, we are approaching 4, and then this is root of x minus root of y plus 1. And then now we're going to have x minus, I'll write this as y plus 1. I've factored out a negative. Now observe that now we have an x here, we have an x here. The difference is square root. We have y plus 1, we have y plus 1. Again, the difference, there's a square root for that term. Once you see this, and especially if you do have, the sign on the middle might not really be very important, but you do have the same format on top, the difference is one of them has a square root. It might be possible for you to make things cancel out, but will it actually be possible? Let's proceed with it and see how it's going to work. So as I said, we're going to rationalize that numerator. To rationalize, we are going to multiply it, both the numerator and the denominator. So as I'm doing this, I'm actually still puzzling it through because I think I've identified another problem I'm going to encounter very soon. So I'm thinking, is it going to resolve on its own? So I'm going to have root of x plus root of y plus 1. Yes, it will resolve on its own. I've just seen how it is going to resolve on its own. Is it? I think so. That. Okay, we'll see. Let's proceed. Over root of x plus root of y plus 1. So in this case, we know to say it's basically just going to be the first term for the first part, because this is going to be a difference of 2 squares. It's going to be the first term squared multiplying the second term squared. So the first term squared, we're going to have x, because the square root is going to disappear, minus the second term squared there. This is also the square root is going to disappear, y plus 1. In the denominator, we're seeing very little is going to happen there. We're still going to have x plus y, or x minus there, plus 1, multiplying the root of x plus root of y plus 1. So this is what we have. Well, we haven't really solved our problem. This part still gives us 0 if we tried to substitute. But something else has become possible. See, when I was starting this statement, I was thinking, we haven't solved our problem, but we actually have. Do you see how? I'll rewrite the same thing. I'll not change a thing. Root of x plus root of y plus 1. I was doubting Thomas, but then now I believe I've just seen how it works out. This is x minus y plus 1. Look at the numerator, x minus y plus 1. This is how our function has reduced to b. What happens here? Don't you see that this is the same as this? It's like this is A, meaning even this is A. Let's take this to be B, meaning as A over A times B. What happens in this case? A and A cancels. Only B remains. Do you agree there?
Yes. Yes.
So meaning our expression actually only gets to remain as 1 over root of x plus root of y plus 1. So the limit we're evaluating has reduced to just that. When you were saying rationalizing the numerator, did you see that it was going to reduce like this?
Like I saw it.
Ah, nice. Now it is continuous at the point. This will be 2 plus 2, and we get 1 over 4 as the solution. That was interesting. Hope you did also find that interesting. Let's see if we can solve another.